Hello, my name is Yahui Zhang from Calibration Group, University of Amsterdam. Today I present a paper, Automatic Calibration of the Fisheye Camera for Egocentric 3D human pose estimation from a single image. Due to the large field of view, Egocentric 3D human pose estimation has valuable applications such as VR and AR. Recent works propose methods for Egocentric 3D human pose estimation and a fisheye camera, aiming at solving self-occlusion problem. However, the negative impact of image distortions on 3D pose estimation still remains. The goal of the paper is to regress 3D human geolocations in the camera coordinate from a single image captured by a fisheye camera. To alleviate the negative impact of image distortions, we propose an automatic calibration module. Figure 1 shows the general procedure to achieve the task. It can be seen that our automatic calibration module estimates the camera parameters. Then they are used to enforce the 3D pose to be consistent with 2D ground truth and image distortions. Therefore, the negative impact of image distortions is alleviated. Here we give a definition used in the paper. Figure 2 shows the imagery model of 3D to 2D projection. Specifically, human pose is represented by a set of joints. Then we take a joint as an example to introduce the difference between two different camera models. First is the pinhole camera model. It is to project uppercase J to lowercase go. There are two steps from equation 2 to 4 to obtain 8. We can summarize the process using equation 5. This slide shows the fisheye camera model that is to project uppercase J to lowercase j. There are 4 steps to compute 8. Specifically, the first 2 steps are to calculate the angle of refraction, which is decreased from theta to theta d. Step 3 and step 4 are to compute 2D projections in the pixel coordinate. Finally, we can summarize the process using equation 15. Compared with the pinhole camera model, equation 15 includes the theta d, which is related to distortion parameters. Therefore, we need to take distortion parameters into account. Then we analyze the factors that affect the reprojection error by the partial derivatives as shown in equation 17. We plot the curve based on the equation for beta visualization shown in figure 4. We find that the level of image distortions has effects on the reprojection error. The larger the value of x or z, the smaller reprojection error. Based on this analysis, we determine the optimization function, that is equation 18. Then, we give details of the updated strategy. According to our analysis of the reprojection error, there are 3 factors that influence the reprojection error. Therefore, we choose L1 loss instead of commonly used L2 loss for estimation of camera parameters. The reason is that L2 loss will make the optimization process focus on lower body and the joints with large distances to the optical axis. Figure 5 shows the overview of our architecture. We first use a 2D pose module to detect 2D pose with heat map representations. Then we have 2 branches. The first branch is an automatic calibration module to predict camera parameters, while the second branch is to estimate 3D pose. Finally, we project the 3D pose to 2D pose using estimated camera parameters. Equation 19 is the overall loss function, including heat map loss, 3D pose loss, and 2D projection loss. There are 2 public datasets for evaluation. However, they include images with the same distortion, which cannot test the effectiveness of alleviating the impact of image distortions. Therefore, we synthetically add image distortions on XR equal pose dataset using equation 11 and 12. Figure 6 shows the example images with the different levels of image distortions. Table 1 lists the comparison with existing methods on the modified XR equal pose dataset. It can be seen that our method achieves the best performance in all activities and also obtains better performance than our method without using automatic calibration module. Then we test the updated strategy on the modified dataset as reported in Table 2. We find that the error of 2 kinds of joints are reduced significantly by our method. The first is lower body, and the second is joints with large distances to the optical axis. We also conduct experiments on current datasets, as shown in Table 3 and 4. Our method performs better than existing methods for 3D human pose estimation from a single image. Figure 7 shows the virtual results on the modified dataset generated by our method. Finally, we give a summary of the paper. We propose a method for egocentric 3D human pose animation from a single image captured by a fisheye camera. We introduce an automatic calibration module with self-correction to mitigate the effect of image distortions for robust 3D human pose animation. Our network shows state-of-the-art performance on the modified XI GoPro dataset containing images with different levels of image distortions. That's all. Thanks for watching this video.